Hello, everyone. My name is Sebastian Manesco. I'm a senior research engineer with Quantstamp. We're a crypto native company based in San Francisco, and we offer world-class security and enterprise blockchain solutions. Today, I'm going to be talking about a topic that is dear to me, that is detecting denial of service vulnerabilities caused by gas limits, as well as generating exploits and fixes for such vulnerabilities. And this is joint work with the University of Waterloo, with the group of Professor Vijay Ganesh. And let's get to it. So for those of you who are less familiar with smart contracts, they're basically programs executed on a virtual machine, in this case, the Ethereum virtual machine. And calling functions of these smart contracts basically changes the state of the Ethereum virtual machine. And this state can record things like balances and flags and all sorts of values. Um, that's why state changes often involve transfers of funds. So when I execute a function, maybe this function would be called transfer, it's going to subtract the balance from my account, and it's going to increase the balance of another account by the same amount. However, these programs, and hence these smart contracts, contain bugs. And exploiting bugs in smart contracts immediately leads to either stolen or frozen funds. So this is very different from classical web development, for instance, where if there is a bug in a simple website, what the consequences of that might be would be something like defacing the website, writing something silly and causing embarrassment of the website owner. In this case, if someone has a bug in their smart contract, they will immediately lose funds, which might not only be their funds, but it would be the funds of their users. So bugs here should be taken very seriously. Now, on the other hand, the Ethereum virtual machine has this notion of gas, and it basically uses a gas mechanism, which is pretty simple. So the idea here is that in order to execute a function of a smart contract, the function caller, so the transaction sender, needs to pay an execution fee. So it's not for free. And this execution fee is computed by multiplying the price of gas times the gas which is consumed by executing those instructions inside of that function. The gas price fluctuates, and also the transaction sender can decide on a certain price that he wants to set. Maybe he wants to set a higher price in order for the transaction to be mined faster, um, or a lower price if he doesn't mind waiting longer. However, the gas consumed is determined by the actual code. Um, and, um, oops. And basically, in order to prevent denial of service at the Ethereum virtual machine level, at the network level, there is this notion of block gas limit. So each block that is mined on a blockchain has a certain limit of transactions that of code or of functions that it can call. And if the gas consumed by all those functions uh, goes over the block gas limit, the transaction will revert and it will not be executed, included in the block. This mechanism, as I mentioned, prevents resource abuse. If like a developer would write a function that contains an infinite loop that would never end, um, if this measure, this security measure would not be in place, it would actually cause a denial of service for the Ethereum network itself. So other users of the network would not be able to participate and call other functions because the EVM would be busy executing that function with an infinite loop. So it makes total sense to have this protection mechanism in there. However, it may cause denial of service at the smart contract level, because if you hit this kind of block gas limit, your transaction might be reverted. And if this happens during, for instance, um, withdrawal, then your funds are frozen and you cannot withdraw your funds anymore. And of course, like, frozen funds are lost funds. Now here's a very simple example of a function written in the Solidity smart contract programming language. And it's called push interest payments. And this is a naive way in which, for instance, smart contract like that simulates maybe a bank would push interests to the end users, to the clients of that bank. It basically has a for loop that iterates over each user in the users list. And for each user, it performs some kind of computation to determine what's the deposit, how long have they kept their deposit. Maybe they have multiple deposits in there placed at different periods of time. So you need to compute the interest for each of those deposits, add them up. And basically at the end, you should send that interest to each user. So this last line here basically calls a transfer function that sends this interest value to each user. Now you may have noticed that the length of the users list is actually controlled by the users of this smart contract, because everyone who joins basically increases the length. And a certain malicious attacker could have multiple accounts, and he could use all of those accounts to simulate new users. And he could increase this length up to a point where the computation in the loop, so the entire function, would reach the block gas limit. And at that point, um, no more users would be able to receive their interest, because, as I mentioned before, the transaction would hit the block gas limit and it would revert. A very famous example, real world example of such a vulnerability in the real world was um, the governmental smart contract, which basically required users to participate, and a certain user would be picked to win the jackpot. That So each user would participate with a small amount of ether, and at the end, a certain user would be picked to be the winner, and he would receive the jackpot, which was around 1,100 ETH. And the code that was used to pay out this jackpot um, used the following two lines of code. Now, this looks fine. It doesn't look like it contains any loops. However, the compiler which they used at the time was compiling this to code which actually contains loops, iterates over the storage locations and detects them one by one, and deletes them, sorry, one by one. So the list of creditors was so long that it was reaching the block gas limit. So there were so many participants that doing this deletion one by one was reaching the block gas limit. Now, this is the source which I used for explaining this, and you can read more there. And the consequences were that the jackpot funds were frozen, so no one could withdraw the funds at that point in time when they were supposed to. Luckily, after the next hard fork, which happened a few months later, um, the block gas limit was increased, and it was increased to a certain amount that was allowing this smart contract called governmental to pay out the jackpot. So there was a happy end, but In case there were more users, this might also be frozen. This could also be frozen today. Just to give you an idea, here's what the block gas limit history sort of looks like. So um, at the beginning, it was somewhere around 3 million. It was increased mostly, it changes mostly when there are hard forks on the Ethereum network. It was increased close to 5 million um, back in 2016. Then it dropped again, and now it kept increasing since that point in time. It kept increasing, and today it's somewhere around 10 million. On the other hand, you cannot really manually check each smart contract whether it has such an issue, because as we see here on this slide, the number of distinct addresses, not all of which are, of course, smart contracts, but we know that there are millions of smart contracts anyway on the main network. They are not feasible to manually check, and this number is growing. So in this work, we're planning to implement a tool that can automatically do that and can also propose fixes. And this came about when we saw that during the security audits that we perform at Quantstamp, we noticed that there are several projects that still contain these kind of gas usage issues. So there are functions in those projects which are critical, and they run out of gas if a certain number of users are assumed, or if certain inputs or certain parameters of the contract are reached. Now, in the current state of the art, it's quite easy to detect such concerns. There are freely available tools, scanners, which can easily detect that there's a loop which either has an external call or does maybe heavy computation and could run out of gas. The problem is, what should you do after you detect? One possibility is, of course, that you re-engineer everything and you do not use loops at all. And of course, that's ideal. However, if that's not possible, either due to technical constraints, time constraints, whatever, one thing that you can do is to perform a gas analysis and determine exactly the point where this kind of out of gas situation, this potential denial of service occurs, and you can add some kind of checks, maybe require statements, asserts, something like that, that would prevent this from happening, and it would notify the user from the very beginning, before any code is executed, that, hey, the state in which the contract is in, or the next state, or the inputs that you provided will lead to an out of gas error, and it could sort of be a preventive measure. This kind of gas analysis is done manually. It's potentially lengthy to perform. There's no necessarily standard process to do that, and it could be very tedious. Therefore, what we want to do in this work is to automate all of that, to just have like pretty a push button solution for that, in order to detect what that gas limit is. And there's several challenges to this kind of idea of automatic exploit generation. And the first challenge is not necessarily very difficult, but the question is, how are we going to detect the exact gas usage during execution? Are we going to estimate it, or are we going to do it at a sort of like runtime? The second question is, like, in such a large search space uh, that the inputs of functions have. For instance, if you have an input which is of type unsigned int 256-bit, the search space for those numbers is quite huge. Also strings, also addresses. The search space is very large. So you don't want to enumerate all of those different values in order to find the right value. So we need to do it somehow smarter. And there's another problem. It's not that these issues, they're not always isolated in just one function in the smart contract. They could be spread across several functions that need to interact with each other first, or that they need to be called first in order to trigger such an out of gas issue in a different function. And we're going to see examples for each of these things. So in the next slides, I'm going to go over each of these challenges, and I'm also going to show examples where it's appropriate. The first challenge was determining the exact gas usage, and there's definitely multiple approaches thanks to the tooling available out there. For instance, there's Web3, which offers this very handy estimate gas function. There's also this predefined function in Solidity called gas left, which tells you how much gas you still have left until you reach the block gas limit. And there's also others, but these would be sufficient, for instance, for our purpose. The second challenge was the large number of inputs, right? And one approach, which is very popular when you have a large number of inputs, is fuzzing. Now, fuzzing has many different possible fuzzing heuristics. These are basically search heuristics. And the slowest one is brute forcing, right? So you basically randomly pick different values in the hope that you will reach the right one. And of course, if the search space is very large, this might take a very long time. Another approach, which is faster, but is not always clear how you can apply this, is divide and conquer. For instance, if you have like a fully ordered set of values like numbers, then you can basically take an interval of numbers and you start from the beginning and the end, and you split it in the middle, and you continue recursively maybe on each part, and you can do like a divide and conquer approach, which is faster in order to reach the right number in a smaller number of steps than brute forcing. However, if you have values which are not clear how you would partition them, right? If you have either strings or data structures which are more complex, it's not necessarily clear how these would apply out of the box, like a push button solution. And this brings us to the approach that we're going to take, which is reinforcement learning. And this is more generally applicable than divide and conquer, and it's also fast. Now, one thing I wanted to say before jumping into reinforcement learning is that there could be other possible fuzzing heuristics. I'm not saying that these are the only ones. There's probably other people working on this kind of problem and have other ideas. It's just one approach which we thought would be appropriate, and we're going to dive into. So reinforcement learning. The approach is basically modeling the problem that we have as a Markov decision process. And for a Markov decision process, you need four things. The first thing is this set of states, which we call here S. And we just take these pretty easily, all the states of the EVM. So any state of the EVM is a state in our set of states. This is more interesting, the set of actions. Now here, actions could be something like calling a smart contract function, choosing a certain inputs for those smart contract functions, increasing, decreasing the inputs of those functions. And this is basically where the secret sauce lies, right? So you basically need to properly choose these actions such that your reinforcement learning algorithm, by applying these actions, learns something and can repeatedly apply these actions and obtain the same results. The third thing that you would need in the Markov decision process is the probability that if you execute an action in state S, you reach state S prime. And since the Ethereum virtual machine is fully deterministic, this probability is 100%, so it's equal to 1 here. And the last thing, a very interesting part that you need in a Markov decision process is the reward function. And the reward function is applied on a certain state. And in this case, it's a state of the EVM. And we want to determine how much gas we have left in that state, because our goal is to reach the block gas limit. Therefore, we have this function here, 1 minus the gas left divided by the block gas limit, which we are trying to maximize, right? So we're trying to bring this value as close as possible to 0, because we want to reach the block gas limit, right? Right, so here's the first example. We have a function which is called sum. It takes as input an integer, an unsigned integer n, and it's a pure function, so it doesn't do any state changes. And we're going to have a loop inside of this function, a for loop, which just sums up all the integer values starting from 0 up to n into this variable called sum, and it's going to return the sum. Now, if n is large enough, this function is going to run out of gas. It's going to reach the block gas limit, and it's going to revert after wasting all that gas. So the goal of the reinforcement algorithm here is to find a large enough value for n such that this happens, and also not just any large value. It needs to find the value which is going to start causing this. So a lower value than it needs to find is going to work. It's not going to revert. And a higher value is going to cause a revert, right? This is the challenge here, finding the exact right value where this kind of out of gas issue starts to happen. Here's another example, which is slightly more complex. It's again the sum function. It has two input variables now, input parameters, n and m, which are both unsigned integers. And before doing the sum, it basically does some computation with n and m, right? So here in this case, it's doing a division of n by m, and it's using the result of that division as the bound of the loop, right? So you can notice here that the goal changes. The goal of the reinforcement algorithm changes. It doesn't need to just find a large value for n. It also needs to find a small enough value for m, and m should not be 0, otherwise there's a division by 0. So there needs to be a certain, it's like multi-goal optimization, right? It needs to find several things that need to fit in order for this function to run out of gas. And here's a third example, which is quite different. Here we have a contract which is called vulnerable, and it has a list of entries. These entries are just unsigned integers. And there are several functions. The first function that you see here is called add entry, and it basically just adds the integer entry that is given as an input parameter, so e. It adds it to the end of the entries list. And the next function which you see is called get entry, which gets the entry at the index I of the input parameter that you give it, like I. And the third function just performs a sum of all entries in the list. So you might already have noticed that the third function is prone to these kind of out of gas errors, because it has that for loop that depends on the entries list. However, differently from the examples that I've shown before, this function, sum entries, does not have an input parameter that can be controlled by the user. Instead, the length of the entries list is controlled through other functions like add entry. Therefore, the goal of the reinforcement learning algorithm here would be to generate a trace that has the following form. So it has a lot of calls to add entry, and then a call to some entries. And this would trigger the out of gas inside of some entries. So just calling some entries at the beginning when there's no entries will not cause an out of gas error. So you first need to set the state of the EVM such that there are enough entries to cause that kind of error. And therefore, the reinforcement learning algorithm needs to find the value of n here. So I'm just showing n, but this n needs to be a concrete number, like 100, 1000, something, that is going to cause the sum entries function to run out of gas. The challenge here is how to determine which functions in a smart contract are going to be affecting the loop boundaries of the functions that are prone to out of gas errors. And the solution that we propose for this is to use something called reverse taint analysis and then forward taint analysis. So I'm going to explain what taint analysis works, how taint analysis works. It's a form of information flow analysis. You basically taint or tag a memory location. It could be a variable, it could be something else. And then you trace the flow of the tainted memory during execution. And you determine all the affected lines of code and all the affected values in memory that are touched by this tainted memory location. This kind of information flow could be either explicit, where there's something like an assignment. The value of X explicitly is transferred to another variable. It could also, this would also happen if there would be X added to Z, for instance, and then assigned to Y. It will also be explicit. And implicit is the case where X would just be used as Boolean, inside of a Boolean condition for a branch statement, such as an if or a for or a while loop, something that is a branch. And inside of the branch statement, there would not be something that necessarily depends on X, right? I'm going to show an example in the following for this as well. Now, here's an example of reverse taint analysis. You basically start from the last executed instruction, which contains your tainted or tagged memory value, and you go backward. That's why I'm showing here this arrow from bottom to top. We start where the last code comment is. So it says start here by tainting bound. And it's because we're tainting the variable called bound, and we're going backwards. And you can see a comment in green for each line, which is basically tainted due to this bound variable. And here, for instance, the value of n is tainted in reverse. The entry's length is tainted here explicitly. But also we have an explicit tainting because we have the n variable and the entry's length inside of this if statement. We also have a tainting of the constant 0. And using this, we see that the function input is tainted. So the variable n, which is the input of this function called sum entries, is tainted. And also the state variable of the smart contract is tainted. So the entries list at the top of the code snippet is also tainted if we do this kind of reverse tainting approach. Now, after we've done the reverse tainting, you remember I said we're going to do a forward tainting. And here we start before the execution. We taint memory values. And since we did the reverse tainting before, we know that the list of entries, so the list of unsigned integer entries is tainted. And we also know that the input of the sum entry function was tainted, right? So we go now in the direction of the execution with the taint analysis, and we see that inside of the add entry function, we have this push method. And because this push method affects the length of the entries list, it's going to be tainted. Therefore, this function is a function that affects the length of the entries list, which we are interested in. Therefore, we know to tell the reinforcement learning algorithm, hey, you should be calling add entry in order to reach a state where it could cause the sum entries function to run out of gas. On the other hand, the next function on the slide here, called getEntry, does not affect the length of the entries. It merely just returns an index out of the entries list, and it does not increase or decrease the length of that list in any way. Therefore, the reinforcement learning algorithm should not be wasting time calling this getEntry function. So what do you do once you know when the out of gas error occurs, right? I've hinted to this earlier. You basically start fixing the code, right? And here I'm showing how a sample fix would look like in blue. This require statement at the beginning of the function would basically check that the value of the input parameter is lower than the certain bound, which was detected by the reinforcement learning algorithm. And it would tell, if this is the case, it would tell the user, hey, this value is too large, you should pick a smaller value, otherwise you're going to run out of gas. For the second example, you could place the require statement after the computation is performed in order to save. You would waste a bit of gas on this computation, which is the division. However, the large amount of gas which would be wasted would be inside of the for loop. So you could place this kind of bound here using a require statement, and you would say, hey, this bound is going to be too large, so you should pick different values. For the third example, we're not going to be placing the fix inside of the sum entries function, actually, like we did before, the functions that contain the for loop in the other examples. Here we're going to be placing the fix inside of the add entries function. And we're going to say that you shouldn't be adding more entries because that's going to lead to an error inside of the sum entries function, right? So these are sort of just like sample fixes. And this is what we're aiming for with our tool, right? We want to not only detect those kind of boundaries, we want to help smart contract developers be able to have a fix in case these kind of vulnerabilities appear in their code. In conclusion, just want to summarize what I've been talking about so far, is that loops inside of smart contracts could cause out of gas errors. Sometimes you need those loops, you can't do without them. And unfortunately, these out of gas errors could lead to frozen funds. And as I mentioned before, frozen funds are lost funds. Now, detecting these kind of out of gas errors is easy at the moment. Because there are freely available tools that do this quite accurately. However, determining the exact values or the exact state, the circumstances in which this error would occur is hard, right? And this is what we want to help build is a fuzzing methodology which uses reinforcement learning and can generate this kind of, that can determine the exact input faster and in a more general way. And in order to do this, we're employing taint analysis in order to guide the fuzzing algorithm, the reinforcement algorithm, as to which actions to perform, which functions of the smart contract are relevant and which are not, in order to save time and learn faster. That's my presentation. Thank you very much. And if you have any questions, here are my contact details. Please feel free to contact me anytime. I will be happy to answer questions. Thank you very much.